After having a hot tea, everybody is refreshed now, and we'll start the next session. And Sri V. Mughal to come to the dais and start the proceedings. The next paper is examination of the influence of physiochemical parameters of coal on gross calorific value, a case study from southeastern part of the Mand Raigad coalfield, Raigad district, Chhattisgarh. And I request Bibhas Karmakar also to come over here for his presentation. So please, Mr. Dr. V.A. Mende and V. Mughal, please come to the stage. Ms. Rajni Ji Dharme, that is delineation of southeastern basinal boundary of Pench Valley coalfield, a case study from Bamanwara sector, Pench Valley coalfield, Madhya Pradesh. So I request her to come over here and start the proceedings and her presentation.
Good evening all. Myself Rajni Dharme, working in Geological Survey of India as a senior geologist. And today my topic of discussion is delineation of southeastern basinal boundary of Pench Valley coalfield, a case study from Bamanwara sector, Pench Valley coalfield, Madhya Pradesh. This is the Gondwana basin of peninsular India. Total 3 main Gondwana basins are present in the peninsular India. This is northwest southeast trending Pranita Godavari basin, then Mahanadi Valley basin, and east-west to east-northeast, west-southwest trending Koel Damodar basin, Sun basin, and Satpura basin. The rhombohedral shape of Satpura basin is a rift valley demarcated by Sun Narmada South Fault and Tapti North Fault in the central India. It extends over an area of vast tract in the south of Narmada plain of Hoshangabad, northern Chhindwara, and northeastern Baitul in Madhya Pradesh. The earliest discovery of coal in Satpura region was made in Sonada area of Tawa Valley by Osley in as early as 1827. The major coalfield explored in Satpura region is Pench, Kanhan, Pathakeda, Gurunda in the southern part of Satpura basin, and Mohopani. This is Mohopani in the northern part of Satpura basin. This is the latest geological map of Satpura Gondwana basin after M. Mahajan et al., which shows the stratigraphic disposition of various formations of Gondwana, of lower Gondwana and upper Gondwana. Overall trend of sedimentary strata in this region is east-west to east-northeast, west-southwest. Then as we go from southern south to north, we have basement here, which is followed by Talchir formation, overlain by this Barakar formation. Then this is Motur formation and this Bijori formation. All these from Talchir to Bijori, it comprises lower Gondwana. And then we have multi-storied Pachmari formation, Denva, Bagra, and at the east and west corner we have Jabalpur formation. It comprises upper Gondwana formation. This is the stratigraphic succession of Satpura Gondwana basin. Entire sedimentary Gondwana package is of about 5 to 5.5 kilometer. Talchir, we have basement of granite and tonalite gneiss, which is unconfirmably overlain by Talcher formation of approximately 500 meter, which is overlain by approximately 450 meter of Barakar formation, then approximately 900 meter of Motur formation, followed by 1450 meter of Bijari formation. It constitutes lower Gondwana, and then Pachmadi, Denva, Bagra, Jabalpur, it constitutes upper Gondwana. Then in our study area, this Gondwana formation is covered with the Deccan traps. This is the Pench, Kanan, Tawa Valley coalfield. Recently we are working in this eastern part of Pench Valley coalfield. Then this is the status map of exploration carried out by GSI. Since 25 years, GSI is working in Pench Valley coalfield. Earlier it is thought that Pench Valley coalfield has been ended here, but after working from 10 to 15 years, GSI has proved the existence of Pench Valley coalfield below the Deccan Trap in eastern and northeastern part. And in the recent year, that is during 2018 to 2023, we have carried out exploration in Bamanwada sector, Sagonia sector and Andol sector. This is the map of geological map of Bamanwada sector in Pench Valley coalfield. This area has been taken for exploration during the year 2017, and total 13 boreholes have been drilled here with the 5,000 meter of total drilling. Then, which founds that the thickness of Deccan Trap is around 200 to 300 meter, which is followed by 10 to 50 meter of Jabalpur formation, which is underlain by Motur formation of nearly 50 to 300 meter. Motur formation is represented mainly by claystone and fine to medium grain sandstone. This is followed by Barakar formation, which is mainly 25 to 75 meter thick. The interesting thing here is that as we move from Tawa Valley to Pench Valley coalfield, that is from west to east, the argillaceous fraction which is found in Motur formation is less in Tawa Valley, but as we move towards east, that is in Kanan and Pench Valley, argillaceous fraction has increases, and it becomes almost 80% in Pench Valley coalfield. Then thickness of Motur formation has also decreases in Pench Valley coalfield. Similarly, the thickness of Barakar formation also decreases in Pench Valley coalfield. This gradual decrease in the thickness shows that we are somewhere in a place where the basin boundary exists. Again, among these 13 boreholes, these boreholes from PBH1 to PBH6, Talcher formation and basement has intersected without intersection of Barakar formation, which again indicate that it is a basinal fault. Then Gondwana sediments of Pench Valley coalfield are in general trending east-northeast, west-southwest to east-west with an average of 6 degree to 9 degree northerly dip. However, in the eastern part of the basin, strike swerves to northeast-southwest, dipping 2 degree to 3 degree towards northwest. Based on the drill data, strike of Bamanwada sector is nearly 10 degree south with a gentle dip to 2 degree to 3 degree towards west. Then this northeast-southwest, we have delineated two faults in this sector. This northeast-southwest fault may be the causative factor for rotation of strike from northeast-southwest to north-south in the present sector, that is in Bamanwada sector. This is the geological section along east-west direction, that is from borehole number PBH6 to PBH9A. This is a section line. In this Bamanwada sector, 2 non-wall faults have been identified based on the subsurface data. Fault F1 is oriented along northeast-southwest, dipping towards north with 70 to 90 meter throw, located at northeastern part of the sector. Then borehole number PBH6 is on upthrown side, that is this PBH6 is on upthrown side and PBH7 is on downthrown side. Then fault F2 trending north-northwest, south-southeast, dipping towards west with the 100 meter throw is restricted in the western part of the sector. This fault is passing between the borehole PBH9 and PBH10. PBH9 is a downthrown side and it is a upthrown side. These are some borehole lithologs from Bamanwada sector. The lateral correlation has been established on the basis of drilled boreholes depicting intersection of talchir and basement. Now, what is happening here that in borehole number PBH 135, we have intersected talchir and basement just below the Deccan trap, but at a very shallow depth. But in borehole number PBH 7, which are at the downthrown side of this northeast-southwest fault, in borehole PBH 7 and 8, we have intersected coal-bearing Barakar formation below Jabalpur and Deccan trap. Again, in borehole number PBH 7, which is at the east of PBH 8, we have not intersected Motur formation. This may be the indication for basin margin fault, because we have not intersected some of the formations here. Now, conclusion. Subsurface data acquired through the drilling in Bamanwada, Sangoria and Endole sector revealed that eastern part of the Pench Valley is affected by network of faults. Strike of fault which are dominant usually trend east-northeast, west-southwest. The northeast-southwest trending fault indicate the basin margin towards southeast. It is established that the intersection of talchir formation as well as basement at shallow depth, along with the non-development of coal-bearing Barakar formation in the eastern part of Bamanwada sector. This clearly delineates the southeastern basin boundary of Pench Valley coalfield is straddling in between Bamanwada sector. Thank you.
Hello. Thanks, Dr. Rajni. We can ask 1 or 2 questions from the forum. Anybody? If there is no question, then we can switch on to next presentation.
Thank you so much.
Nice presentation by. Hello.
Now I will request actually the chairperson, Dr. V.A. Mende. He has one key paper here, but somehow we started the session early, and that is why Rajni Dharme was called for presentation. So I will request Dr. V.A. Mende for his key presentation, that is steam reforming of coal bed methane to produce hydrogen and carbon dioxide, a multi-optional techno-economical approach in enhanced recovery. This is some new modern technology. I think it will be enlighten us. Dr. Mende will enlighten us regarding this. Dr. Mende, please.
Thank you, Sarotkar sir. Yeah. In the chair, the respected Banjara Vadkar sir, and they are the learned, the participants, the delegates, and the research scholars. I am Dr. Mende, and I am working at CSIR Simper since 1997. And since my joining, I am working on the coal bed methane, the coal geology, mining geology, the shale gas, Presently I am working on the oil shale of the northeastern part, and one of the projects to be funded by the ONGC through the Ministry of Petroleum and Natural Gas, that is on the steam methane reforming of the coal bed methane. There is always a question why we should not go for the CO2 CO2 sequestration in our country. For CO2 sequestration, there is a need of the CO2, and if you practically think, as such, there is no commercial CO2 is available, even though we have several power stations in our country. But capturing is a major issue. Secondly, if you talk about the flue gas present in our the flue gas of the thermal power stations, there hardly the CO2 concentration is 12%. Even if you apply any kind of efficient technology to capture it, that hardly capture 5 to 6% of the CO2, and for that capturing you need a lot of the money, and of course because of that the economics comes in a problem. So no power stations in our country is ready to take up this CO2 capturing. For considering this point, of course, because of this net zero emission mission, there is a great means emphasis from the Ministry of the Coal, the Ministry of Environment and Forest, that we have to capture wherever we emit the CO2. So one by one we are going to take up that. But at present, if you want to do any kind of CO2 sequestration in subsurface, we have to find out some alternative the options. And one of the option is the steam methane reforming of the coal bed methane. What exactly it is? There is, I think everybody understand what is coal bed methane, because now it's a well-known term. And in eastern part of our country, we are producing about 3.5 million tons of million cubic meter of gas per day. When we have started this research long back, somewhere in 1996, 1997, that time the plan was to achieve the production of maximum 10 to 12 million cubic meter per day. But because of so many constraints, so many the policy issues, so many the local issues, geographical issues, and the major problem was the infrastructure. The utilization infrastructure we was not having. So recently, in 2021, this eastern part, we have now this. It's not working. So in eastern part of our country, now we have a national grid, and this national grid was not only for the CBM, the gases we produce from the eastern the part, that also comes to this grid line, and from the here Jagdishpur it's come in the Uttarakhand. So from the Uttarakhand to through all the CBM blocks, mostly CBM blocks we have in the Damodar Valley. So there it goes from the Damodar Valley, and then it goes to the Paradweep. And from the eastern parts, it's coming to the Assam, then Bihar, and then Jharkhand, and again it is joining near to Gaya, that Dhobi. So after construction of this pipeline is taken care by the GAIL. Now there is a great emphasis that we should have the large-scale production of CBM. So now there are the numerous operators like the ONGC, then Great Eastern Energy Corporation, then we have Reliance, we have the SR, we have the Dirt Energy, and few more players. They have started drilling of the wells, and at present more than thousands of wells are under production. And in in a couple of years, the target is we should have drilled more than 5,000 of well to achieve that 10 to 12, 10 to 12 million cubic meter of gas. And that 10 to 12 cubic meter of gas is a 10 to 12% energy requirement of our country. Always you might have heard or seen in the television, and now our the transport minister, Mr. Nitin Gadkari, always says that we should switch over to the green energy. So hydrogen is considered as a green energy, but what will be the source? Where we can get this? So at present, the most of the hydrogen which we are getting, that is from the natural gas. So thermal destruction of the natural gas is the prime source of hydrogen generation. Apart from, but that hydrogen production is not sufficient what we are going to, the demand which will be coming in a near decade. So considering this, there are as such for the hydrogen production, there are different technologies like the reforming of carbonaceous sources, the fossil fuel, from that we can obtain the hydrogen. Then another option is a biomass pyrolysis, that is biomass gasification, and then gasification of the biomass and the coal. Then electrolysis of water is a well-known technology, but because of the high economics, that is for the large-scale production, there are the great issues. Then few more like the biohydrogen process, then thermochemical splitting of water, then coal and coal biomass gasification, underground coal gasification is also coming. Very soon we have already got signed an MOU with the Adani Group, and Adani Group has awarded, given us 2 blocks in a Chhattisgarh. One is Jhigador and another is Khadgaon near Ambikapur. And there we are going to demonstrate this underground coal gasification technology. And it will be a first project in our country for the capacity building. There are the multi approach and multi benefits of the from methane to coal bed methane to hydrogen production. In coal bed methane, when we produce from the coal, the methane comes maximum 99%. But in some of the coal seams which are immature or having a thermal influence because of the igneous intrusive, or the CBM which we are producing, or which we will be planned to produce from the tertiary basins like the western part of our country, that is the Mehsana, Gujarat, or the Barmer, Sachor, or southern part of your Neyveli, Nagapattinam, or Kumbakonam, or Mannargudi. There what we found when we analyzed the gas of the CBM, there more than 25% is CO2. So what we have planned, that why not to capture that CO2 and inject in a reservoir for the enhanced recovery. The operator is ready. Why? Because CBM, if you sell in a market, you hardly get 80 rupees per kg. But when you convert it into hydrogen, the price of the hydrogen is 4 times. At present, more than 380 rupees. Then the second thing is CO2 you are getting ready-made. Other option, other benefit is the other benefit is your hydrogen has a calorific value 3 to 4 times more than your methane. Methane hardly, if it is a pure in 99%, then its calorific value comes around 13,000. And in CBM, we hardly found 8,500 something. And in pure hydrogen, the calorific value is more than 33,000. Even if you produce from the steam methane reforming, the value comes about 30,000. So calorific value also is very high compared to the methane. So considering this option, this is just a basic design how the CBM is produced. We will be producing CBM suppose one example I am telling you, that is the East Bokaro of the Damodar Valley. There ONGC has already drilled more than 120 wells, and some of the wells because of the under saturation or because of the moderate saturation, even after pumping a continuous water, the gas is not coming out. So they have given those wells to us, and those wells we are using for the CO2 injection. Methane on the surface we will be having the steam methane reforming engineering construction. It's a kind of just a cooker which will maintain a temperature of 700 to 800 degree, and methane produced from the coal seams will be injected through that cooker, and it will be through the thermal destruction it will separate, and during that process the water gas shift reaction will also be done. So first when you break that CH4 bonding, CO and 2H2 will form, means, and then in water gas shift reaction that CO will be converted into CO2 and the 2H2 molecules. So here when you generate 1 molecules of CO2, 4 molecules of hydrogen we are getting. So this is just the engineering structure. Here this kind of well we have on the surface, and this will be a gas gathering station, and through the thermal destruction this is also a compressing station, and it will be thermally dissociate and it will be injected in a reservoir. Why the advantage of this, just James have already said that there is already a classification of the kind of hydrogen, and that is based on the type of source, the type of process and technology you are used. So here steam methane reforming is through the blue hydrogen. So based on the what kind of source you are using, the hydrogen is categorized. So if you look at the economics, hydrogen production is quite cheaper through the steam methane reforming. Cost wise, you see, if you use the coal, here is the steam methane reforming, and other all are expensive one. Here also the steam methane reforming efficiency is very high, then carbon footprints, that is also very low. If you look at the global hydrogen demand, the demand is continuously increasing. Of course, we have to work on the storage. I expect there will be some questions on the how the hydrogen will be stored or transport. But at present, being a geologist, I am more focused on the genesis matter. This is well known that how these different CBM blocks, about 32 CBM blocks already been awarded, and out of them 7 blocks are already production, and in near coming 5 years we are expecting few more blocks, 10 to 15 blocks will be added under production. So drilling point of view, in Raniganj East we have already drilled 460 wells, and in Raniganj South 360 wells, Jharia 16 wells, in Bokaro, this is the latest information, 105 wells, and North Karampura 81 wells, and Sohagpur East 100 wells, and Sohagpur West 100 wells. So the operators are continuously drilling the wells. So if you take the example of the India, so there are 4 the technologies we have identified which will be suitable to produce the gas in India. That first is the renewable, that water electrolysis everybody is using, but of course the economics is the major issue. Biomass, being an agriculture country, we have a lot of agriculture waste. That agriculture waste, through the gasification, we can obtain the hydrogen. The natural gas is very well, this steam methane reforming of natural gas is a well-known process, and wherever we have these refineries, there we are producing the hydrogen. And coal, the surface gasification at Simper, we have a pilot scale plant for the fluidized gasifier, and most of the issues related with the gasification we have resolved, and we have obtained a maximum of 40% of hydrogen through a fluidized bed gasification. Now coming to the the geology part, why the CO2 sequestration? CO2 has an affinity 3 to 4 times more in a coal or any kind of conventional, unconventional, or any kind of gas reservoir. Wherever we have organic or inorganic, or even the shale which has a large amount of clay, there we can inject a CO2, and if the gas is there, that gas can be taken it out, because when you inject a CO2, CO2 gets stored and it just replaces the methane and the kind of hydrocarbons available there. At CSR Simper, we have a high adsorption isotherm facility. There we have already proved that the methane adsorption capacity maximum of Indian coal, the Gondwana coal, we are getting 12 cc per gram, and the CO2 when you inject, that is more than a double. Now the major constraints of the CO2 sequestration in any kind of reservoir, when you inject CO2 in a reservoir, what happens? That particular coal, shale, or the rock gets swelled, and because of that swelling, whatever the permeability, because the reservoir is directly the gas recovery from the reservoir directly depends on the permeability. Permeability is is a primary parameter for the gas recovery. So when you inject a CO2, your reservoir rock gets swelled, and because of that swelling, whatever the fracture or whatever mechanism you have in a coal, that gets jammed, and the flow of the gas is lost. So how to optimize that? So at CSR Simper, we are developing this laboratory. So through this the equipment, we will be measuring when you inject a CO2 and allow it to saturate in a pores of the coal or shale and the rocks, how much it gets well in a different direction, and how to stop that, how to optimize that swelling. So this laboratory is under construction, and this will be a unique facility in our India. Next thing, once that swelling, the deformation, the data you can correct your permeability model. What exactly happened in the CBM reservoir is, there are two kind of recovery in any kind of reservoir for oil or gas or CBM. When you, in a few years of initial production, because of the reduction of the pressure, there is a slippage occurs between the bedding planes, between the cleat fracture or whatever the mechanism it has, and because of that, suddenly the permeability which you have initially expected or measured, that suddenly gets enhanced, and because of that, the production you are expecting per day, that suppose the 5,000 cubic meter of gas per day, that suddenly get enhanced 25,000, and that is because of the shrink of the reservoir because of the reduction of pressure. And this effect we call in a scientific the term called the Klinkenberg effect. And this Klinkenberg effect suddenly gives you the more gas. But when you inject a CO2, that is lost. So being a scientist, being a reservoir geologist, our role how to optimize that. So when you inject CO2, how the permeability change, and for optimization what we have to do. In our reservoir, we have the different kind of material. in a cleat and fracture and the macropores system. Here you can see in a 200 nanometer scale, in a pore, we have a calcite. So this calcite is a hurdle. But apart from that, the advantage is that even that calcite, there we have the pore system. And this calcite treatment during the hydrofac to enhance the permeability is easy. But if you have the material like the kaolinite, so kaolinite is a silica and it's a hydrous material, and when you inject any kind of fluid during the hydrofac, this gets swell, and whatever the gas flow mechanism you have, that is lost. But if you control it, these books-like structures, these bedding planes, they are the passage for the your transfer of gas. In some of the coal, we have also found some jellified because of this geochemical alteration or because of the thermal effect. The coal gets jellified, and because of that jellification, we hardly get any pores or any permeability. This is good. Here we have in between the grains, we have the pore network, and through that gas can flow. This is the map of the East Bokaro, and we have planned to, this entire block is under CBM production. In between, we have underground and open cast mines, but this block is allotted to ONGC, and ONGC, this particular area is highly gassy, and this part is also highly gassy. So this is the deeper part. Just for the information, I will tell you, CO2 sequestration is at any depth is not feasible process, because CO2 we have to inject in a supercritical pressure, and that supercritical pressure is achieved at a pressure of 80 kg. So always remember, whenever we plan for the CO2 injection, the depth should be more than 800 meters. We should not tell, or we should not inform anybody that anywhere we have a reservoir, even shallow depth, or the coal seam which are occurring at 500 meters, which has a lot of gas, and we can produce. Yes, we can produce gas, and in future we are going to mine that particular coal seam. But CO2 cannot be injected. If you inject there, what will happen? That will come out, or that will haphazardly flow in any direction. So we should always care the depth should be maintained below 800 meters, so that the CO2, the main concept is in supercritical condition, CO2 is dissolved in a groundwater, and that groundwater go in a longer distance carrying your CO2 molecule, and then it get absorbed in a coal or shell or any kind of reservoir. So in East Bokaro, this is the deeper part we have selected at presently ideal, where at below 800 meters we have a number of coal seams which has a thickness more than 10 meters. Those coal seams will be targeted, and this we are going to start from the July. Here we have about 7 billion tons of coal. So the site is excellent, because we are also the learners, and in the beginning itself we don't want to fail. So we have chosen such an ideal site where we have a sufficient gas, and second important thing, the CBM which we are producing, CBM gas has a more than 10% of CO2. So that CO2 will be captured at the surface. So at surface we are going to install the amine-based the plant which will capture the CO2, and that captured CO2 will be injected in a reservoir, and whatever the CBM is produced at present from one well, say 5,000 to 10,000, that production will be increased 3 to 4 times. So like that, in North Karanpura also we have identified one site in the center part where we have a thick coal seams in a bara. Here also we have a large amount of deposit, a maximum of 14.6 billion tons. In South Karanpura also we have identified one site where 6 billion tons coal is available. Before any kind of taking up any kind of projects for the CO2 injection or sequestration or the enhanced recovery, we should gather some basic information, or we should estimate the basic information. So basic information which we have generated for the different coal, different basins. So in Jharia basin, about 71 million tons of CO2 can be injected. So accordingly, at present, the coal field which we are going to take up, there also a lot of CO2 can be injected. Accordingly, we have estimated for each and every coal basins for the CO2 injection, and about 4.4 gigatons, means 4,426 million tons of CO2 can be injected in a CBM blocks. The next important thing, as I said in the beginning, that we have to also find out the different point sources. So initially our target was to have the capturing from the thermal power stations. So for thermal power stations also we have estimated in different thermal power stations. These are the thermal power stations we have in a different coal producing basins or CBM basins. And there, how much CO2 per day we are generating. So I am not reading all. So large amount of CO2 per day we are generating, but we do not have any single project for the capturing. CO2 injection and the enhanced recovery of methane. There are the pilot scale studies already been done by the foreign countries, and these are the 3 important successful demonstration projects, because this technology is mostly in a demonstration stage. Commercially it is yet to be applied. So in USA they have done injection of the CO2 in a CBM reservoir, and they have proved that 77 to 95% of gas available in a CBM reservoir is recoverable through the CO2 injection. So maximum gas can be recovered through the CO2 injection. And in Canada, they have also given a similar kind of results. And Japan also, they have suggested that 90% of injected CO2 stored in a coal seam and more than 90% of methane is recovered through the CO2 injection. This is the pilot scale study done by the US, somewhere here in Kentucky. And they have seen, this is the normal production curve. And when they have injected a CO2, suddenly this production is going up. Just one more curve I am showing. Here you can see. This is the normal production. And when you inject the CO2 after 30 years. Because in US, they have started CBM production somewhere in 1982. We are far behind to them. But we cannot compare our CBM reservoir with the US reservoirs, because the kind of the reservoir or kind of geology they have, that is entirely different. The gas content is low, our geology is, the formations are very old, we have a lot of structural challenges, we have the permeability challenges. So they don't have the challenges which we are facing in a CBM reservoir. So here, after 32 years of injection, suddenly you see the production is enhanced. So these are the few, the other demonstration projects that different countries they have carried out. These are the few critical parameters for the CO2 injection and methane recovery. The first one is the thickness. We should have a sufficient thickness, and depth, I said, it should be more than 800 meters. And there should be a gas and water particular ratio. If you have a dry coal seam, then the injection process will be different. Next thing is, there is always, if you talk in the coal forum,
hello, Dr.
always
Mende.
there is a question.
Hello, please
Just
continue.
1 minute. Okay. Always there is question. You are telling that you will be injecting CO2, and in future we will be going for the mining. What will happen with that? So at present we are conducting a experiment at our laboratory. The injected CO2 will be mineralized in a solid form. Already in our coal we have the active cation like sodium, the calcium, the potassium. So there are different cation anions we have that easily gets react. If it is not reacting, we have to give them some catalyst, and we have to maintain the pH condition of the aquifer, and then we can get it mineralized. So one of the process that is the mineral trapping, which we are suggesting, and for that in laboratory we have already started this experimentation. We have developed the autoclaves, and under that autoclave, it's a high pressure autoclave, we are maintaining the subsurface reservoir pressure and the temperature condition, and the coal, we are injecting a CO2 and the mixture of gases in that, and saturating it and maintaining some pH condition. We are trying to get it mineralized. So kinetics of the CO2 mineralization we are working, and for that, because catalyst importing or having the ready-made catalyst for any kind of mineralization is very expensive process. So what we are trying to say, the kind of different minerals we have, the dolomite, the limestone, the dunite, the magnesite, the different kind of ores we have, or iron ores we have, are they, will they help us to get mineralized the CO2 in a coal or oil or shale or gas reservoir? So there is a great scope for the ECBM in India and CO2 sequestration. So I always welcome that people should work, and the young people, they should work on a shrinkage and swelling, because most of the IITs, most of the research institute, most of the CSIR laboratory scientists, they are working on the general characteristics of coal. When you inject CO2, how much it gets stored. But nobody is working when you inject CO2, how much your coal will get swell, and what about your the permeability and porosity, and how it will be optimized. With these words, thank you very much.
Thank you, Dr. Mende, for your nice presentation on steam reforming of CBM for producing hydrogen and CO2 and its advantages over CBM and the intricacies of the process, though these are in, I think, a nascent stage. So, thank you. Now, it's open for questions, if any, from. One or two questions. No questions? Thank you.
Thank you.
Thank you.
Yeah.
Next presentation, please. Magar on examination of influence of physiochemical parameters of coal on GCV, a case study from southeastern part of Mahandragar coalfield. Dr. Vibhas, please.
Thank you, sir. Dais and of the dais and the participants on this seminar. Myself, Vibhas Karmakar, and now I am presenting examination of the influence of physicochemical parameters of coal on gross calorific value, a case study from southeastern part of Mahandragar coalfield. Coal is a major resource nowadays for electricity generation, and this coal easily available in India. So now from today we have discussed a lot regarding the non-renewable energy resources, regarding the alternative energy resources. But without coal, we cannot generate electricity. So we should think about that. This is the coalfield map of central India, and my mainly concern in this portion. So I am working on the southeastern part of Mahandragar coalfield, and this is the geological map of Mahandragar coalfield, where we have seen the different geological formations, and means Raniganj formation, Barakar formation, Barren Measures, Talchir formations. And this study area, rocks of this study area mainly belongs to the Raniganj and Barakar formations. So this is the geological map of study area where we have seen the numerous faults have been traversed in this area. And why this fault is important for our quality of coal? Because this fault can omit the strata, this fault can repeat the strata, and this fault can increase the quality of coal. So before exploring any areas, we should think about these structures. And these are the surface indications. This is the intense silicifications we have observed in the Raniganj formations in the study area. This is the subvertical fractures we have encountered in the borehole cores, and this is the steep dip of marker horizons that indirectly indicate that area traversed by fault. And so we have collected numerous coal samples from the different blocks drilled by GSI. And we have analyzed that coal samples for proximate analysis and gross calorific value. So according to the gross calorific value, we have classified this rank of coal or grade of coal, that is non-coking coal, up to G17, 1 to G17. So G1 is the highest rank, highest grade of coal, and G17 is the lowest grade of coal. And accordingly, the density of coal also increases. So for this is the plots where we have seen that iso S plus moisture versus seam. So we have encountered total 8 number of seams in this coal field. Mainly thickest seam is the seam 6, seam 7 and seam 8. So in this case we have seen that coal samples belongs to these boreholes and this one, where we have seen that S plus moisture content much more compared to the other boreholes. So due to that, our GCV value decreases. Parallelly, for seam number 5, in this portion, S plus moisture value is less. So compared, due to that, our GCV value is high. This is for the seam number 7, seam number 8. So for seam number 7, this is the zone where we have encountered maximum S plus moisture value. So due to that S plus moisture value, our GCV value is less. This is the relation between volatile matter and gross calorific value. So I have collected all the coal samples from the different coal seams and we have analyzed and I have plotted these data, that is volatile matter with GCV. So from this linear graph, we can see that regression factor is 0.7524. And this is the best fit regression line. So this volatile matter, that is nothing but a mixture of gaseous and liquid products from that thermal composition of coals. And due to this volatile matter, our gross calorific value increases. So we have concluded that here, gross calorific value having a positive correlation with the volatile matter of the coal. This is the S plus moisture value with gross calorific value. So S is nothing but an impurity which will not burn. And it is usually consists of silica, alumina, iron oxide, lime and magnesia. And when high S content present in the coal, that can prevent, that can decreases the quality of coal. So with due to this, when S plus moisture content increases, GCV value decreases. That means there is a negative correlation between S plus moisture with gross calorific value. This is the fixed carbon content versus gross calorific value. So fixed carbon content is nothing but a free state and which does not combine with any other elements. So with increasing fixed carbon content in the coal, gross calorific value also increases. That means quality of coal, that is depends upon the proximate analysis. So if S plus moisture content increases, that means our gross calorific value decreases, so our quality of coal, that is grade of coal, decreases. And that grade of coal mainly used for nowadays thermal industry, for steel making industry and for cement making industry. So conclusion, the proposed correlation studies are showing that the content of gross calorific value is increased with decrease the content of moisture and S linearly. The content of S in coal is impurity present that will not bond. The gross calorific value is also increased with the increase of the content of volatile matter and fixed carbon percentage. The study of gross calorific value correlated with the parameters of proximate analysis and useful for determination of the quality of coal, and also it may be useful for cement industries, thermal power industries, and steel making industries. So the authors gratefully acknowledge the work facilities provided by the GSI, Session Nagpur. Thanks are also extended to all the individuals associated with these projects. Thank you very much.
Thank you, Dr. Vibhas Karmakar, and for your focused presentation on the physiochemical parameters like ash plus moisture, volatile matter, and its influence on the gross calorific value and its correlation. You have presented very well. Thank you. Over to Chairman.
You shown the correlation GCV versus the volatile matter.
Yes, sir.
The GCV versus volatile matter.
Yes, sir.
Will it be applicable in low rank coal, the lignite?
No, sir.
Or
It will not
site-
applicable for
it is
lignite.
Site specific.
It only applicable for non-coking coal.
Okay. Okay. Then in your area. Okay.
Because for lignite, yes, sir.
Question, please.
When fault, that means a disturbance in the area. Why fault occurs? Because of the. Have you proved it? Yes, madam. We have the data.
Sir, madam, it is
in their original structure, microstructure.
Okay, madam, I agree your point. But before.
No, but my point to you is, okay, whether we agree to each other or not, my thinking is this, that when did your faulting appear? When did your faulting take place? During the time of coalification, during the time of sedimentary basin being formed?
No, during
or after the entire thing happened, you had the faulting occurring?
Actually, during the time of after that, vegetable matters goes to your qualification stage.
Bibas,
That qualification stage.
Bibas, question is different. Madam
Yeah.
is asking whether that faulting has been occurred during sedimentation or after sedimentation.
That already I have answered,
The
madam.
question is the same, answer is also same during sedimentation itself and during formation
Exactly,
of coal
that
as
I have,
well.
that-
You reply accordingly.
That question already I have answered. That fault may be during the time of sedimentation or after sedimentation. That fault may be your sin sedimentary fault, or that fault may be after your sedimentation.
Okay, thank you.
Yes.
Yeah.
Pardon? Okay.
What are the faults, what are the tectonic events influence this Gondwana coal? Which are the triggering tectonic impact that leads to your statement that some of the coal is natural?
Actually, during the time of formation of Gondwana, there is a tectonic zone, South Narmada lineament. Okay, so due to that South Narmada lineament, there is a longitudinal fault and there is a transverse fault. So due to transverse fault, one opening is there, a longitudinal fault, another opening is there. So due to that fault, your sedimentation occur in the basin. That fault cannot play a role for the maturation of coal. That fault only for your development of the basin.
Just we will discuss afterwards in this way. Okay, thank you.
Thank you, sir.
Thank you.
Thank you very much.
Please.
Okay, good evening, ladies and gentlemen. My name is James Peters. I'm still a bit active, though I retired from the ONGC in 2011. I started as a sedimentologist, went on to do field geology, especially Satpura. I did my PhD from there also. And subsequent to that, I went to Assam for operations, where I had ample time to read. And while reading the APG Explorer, I came across this issue about coalbed methane being explored in Canada. That was sometime in the late 80s of the last century. And got me thinking, we have coal in Satpura, why don't we look at that? I had the opportunity of going back to the research institute at KDMIP, and my mentors like Dr. S.K. Biswas, Kuldeep Chandra, and others, they gave me a free hand to look into coalbed methane, and I started my entire career in coalbed methane somewhere in the middle 90s. I'm going to go back. I was quite delighted to hear Dr. Mende's presentation on eCBM, especially CO2 injection. Scientifically, I totally agree with him, but commercially, it is yet to be proven viable. Even the chairman also said the same thing in the morning, or sorry, the chief guest said the same thing in the morning. We've got some fields in Gandhar. We're ready for that, but viably, economically, it may not be viable right now. So I'm going to give you a general historic perspective, status of exploration and production, and the future potential of CBM in India. Okay, we have these two curves or two diagrams, pie diagrams, showing the requirement of the source of energy. Presently, coal is around 44%. Pointer. Yeah. Pointer. Yeah, pointer. Around 44%. Hydropower is around 2%. Biomass and waste is 21%. Natural gas 6%. And this is what we are really interested in. 6% today, the government of India is planning to increase it to 15% by 2030. So CBM has been considered to be one of the options that we have to augment part of this increase, not all, only part. If Dr. Mende's scientific eCBM does take off properly and in the right direction, then perhaps we may exceed that also. Yeah. The total supply of natural gas is expected to go at a CAGR of 7.2 from 2012 to 2030, reaching around 474 million standard cubic meters per day by 2930. That is what the objective is. And at present, how does India plan to do it? Is domestic sources. There's a full list out here. LNG imports and cross-border gas here. I'll skip this because everybody knows how CBM is formed. What are the critical parameters? Most of you all know. gas curtain, thermal maturation, permeability, that's cleats and fracture systems, reservoir saturation, adsorption, desorption isotherms, measured by that, burial history of the basin, current depth of the coal seam, hydrology and reservoir pressures. Coal as a reservoir, the gas acts as a free gas or occurs as a free gas within cleats and fracture networks of the coal seams, that's GOB gas. Gas dissolved in groundwater within the coal seams, that's connate water, nothing to do with the freshwater aquifers that we have. Gas held within the matrix, macro and micro porosity dependent on material and composition, and finally the adsorbed molecules on the internal surface of the adsorbed within the molecular structure of the coal. This is the way the gas actually occurs in the coal seams here. This again is how it migrates within the coal seam depending on Fick's law, molecular diffusion through the matrix, and this is all on Darcy's law. Comes to the phase cleats, blood cleats, and the desorption from cleat surfaces. And this is the basic different regimes, flow regimes. We have the stage one is the saturated flow regimes where you have water, then you have water and gas, and then finally there's a gas breakout here. That is how the entire thing actually happens. Basically, a CBM well is nothing but a water well. We get the water out of the tubing and the gas comes out of the annulus. So gas is just a byproduct, but the primary objective. Historically, CBM started way back in 1931 in USA, and in 1950, a lot of attention was drawn to the San Juan Basin of Colorado. The Department of Energy funded a long-term standing research program in the 60s, potential of emission gases as a viable source of energy. And finally, in the 70s, there was a field in Colorado which depleted its conventional hydrocarbons. And as per the Colorado state mines, there was no difference between conventional hydrocarbons and the coal bed methane. So they fractured the coal bed methane, coal seams within that well, within those wells, and they started producing coal bed methane. This basically was a re-engineering project altogether. So there are two things you have to look at it. Either you go for primarily only for coal bed methane, or you think of it as a re-engineering project here. These are the two ways how this entire thing operates here. These are the general resources, worldwide global resources of CBM. Okay, in India, we started CBM, ONGC at least started CBM way back in 1992. And there was a general evaluation of different coal fields for the CBM potential. 1994, we evaluated Satpura Basin. That is when I came back from Assam to the institute. And we took the help of MECL Nagpur and CFRI Nagpur at that time. We didn't have any information on CBM. Nobody knew what CBM was. We knew the coal industry knew a lot of the material, I mean all the parameters for the coal mining, but none of them knew anything about CBM. None of us knew anything about CBM. So our idea was to take all that data, try to convert it into CBM specific data and start looking at things separately. In 1995, SR Oil drilled a well, CBM well in Mehsana. It was not very successful. 1996, detailed evaluation of Durgapur depression was undertaken in Raniganj Basin. We drilled two wells in 95-96, DUA and DUA-B. We did not produce CBM, but we learned a lot from those two wells. It was all a learning curve for us. 1997, by the time we had shifted our entire focus to the Parbatpur block of Jharia Basin, and 1997 we successfully flowed CBM in August. I remember it was August 1997. 1997, the Government of India came up with the CBM policy also. And from 2001 onwards, 33 CBM blocks were given to 8 operators. The geological parameters are listed out here. Presence of adequate quantity of coal at suitable depths, suitable grade, ash contents should be low, suitable type, vitrinite materials should be as high as 55%, suitable rank, all the rank and other things, sorry. You have got the rags, the VROs, that's vitrinite reflectance, the elemental carbon, etc., the permeability that you require to produce CBM at, gas content, which is a very important part, and finally the saturation again also, which is a very important part. India is endowed with a large amount of coal. The 352.16 billion tons of geological coal resources up to a depth of 1200 meters. This is the 1421. And geological resources of lignite stand at 48.02 billion tons. Yeah. This is the different gold fields. 2 minutes more. Okay. Okay, I'll skip all this. These are the economics of scale, and these are categorized. We did categorize coal fields as per different coal ranks. Different parameters way back in 2004. That paper was published in Oil and Gas Journal, and we keep revising it. It has to be updated. It's not a permanent fixed classification. So we have been revising it and seeing as soon as the data keeps coming. We got Jharia, East Bokaro, Raniganj, North Karanpura, Sohagpur, South Karanpura, Rajmahal, Birbhum in category 2, Praneta Godavari Valley coalfields in Ib Valley, Ib River, Mandragar, Talchir, Vardhan category 3, and finally category 4. These are all the tertiary lignites. Okay, this is the general resources and status of operations in India. We've got the various blocks, there are 8 of them, which have been looked at thoroughly. Raniganj East, this is by SR, this is by Reliance, this is by ONGC, this is by GECL, this is by Reliance again, this again Jharia, this is by ONGC and Coal India. This is a joint venture. Raniganj North, ONGC Coal India joint venture, and North Karanpura. This is for ONGC IOC joint venture, but being operated by Prabha Energy. Here are the statistics for all these things. Finally, expected cumulative production in the next 5 years, 21, 22 till 24, 25 is going to be around 8 billion cubic meters, whereas cumulative production till 21 was 4,385 million standard cubic meters. Yeah. Then the rest of it is all available with the DGH website, and presently SR has drilled 348 wells, and they plan to drill 400 more wells in the East Raniganj. Dr. Mendez already given the statistics for East Bokaro. And looking at the north Raniganj, the joint venture between Coal India, between ONGC and Coal India, they are doing something, but there are some logistic problems in that area. Yeah. So with that, because of the time, I just will like to conclude by giving you the different productions of the different oil fields and the cumulative production out here. This is up to 21. We got Raniganj South, GECL, Jharia, ONGC, Coal India, Raniganj East, this is SR, Bokaro, this is ONGC, Sohagpur Reliance. And these are the various figures, the production figures, and this is the cumulative figures for all. Now, in conclusion, what I have to say is substantial resources base exists in India, especially for coal, which could be converted to CBM gases at some point of time. Current exploration and development activities are mostly concentrated within the most encouraging and high-ranking Gondwana basins. The special bid offering by new acreages both in high and low rank blocks by the Government of India ought to bring in new players in the business. Implementation of new policies by the government, the exploration of CBM should get a big momentum. And finally, it is expected that exploration activities may, in many such new blocks, resources will be converted to recoverable reserves and thereby increasing gas production from such unconventional resources and further providing a substantial fillip to the ever-increasing natural gas demand in the Indian market. Thank you.
Thank you. Thank you, Dr. James Peters, for throwing light on history, status of exploration, production, and its future exploration of CBM in India. Now it's open for questions, if any, one or two. No questions? Thank you. Thank you.
Thank you.
And it's we are concluding this technical session 4 with this presentation. I think it will be another technical session 5, that is on coal sector 2. Thank you. Thank you all.
Next session, I invite Professor Mrunal Kanti Mukherjee and Professor S.M. Hussain for the coal resources in India exploration and production. So, Professor M.K. Mukherjee, please. We will be having key paper by Dr. M.K. Mukherjee on prediction of water ingress in an open cast and underground mine excavations. An example from Korba and Mandragad coalfields, Chhattisgarh. This is a key address. So I invite Dr. M.K. Mukherjee for this presentation. Dr. M.K. Mukherjee, please.
इधर नीचे रखिए
इसके ऊपर रख दोगे इसको ठीक है आप थोड़ा इसको
Good evening to all of you, dignitaries on the dais, off the dais, all participants, distinguished scientists, professionals, industrialists, press and media, those who are all present here. In this technical session, I would like to say something about not the energy rather, but how the conventional energy can be safely mined. And an important thing that actually affects all coal mines, this is one coal mine in front of you, it is being actively mined, but you see it cannot be mined. The problem is that the real mining phase is here and the production center is here, but it is not mineable because you can see a lot of water here, which is basically logging up here. And even though these haul roads are basically made for transport of the coal, it is still lying dry because the coal cannot be brought out from the system because it is a huge amount of water which is ingressing. Ingressing means water is seeping inside and blocking the face and increasing in volume with time. Now this is an open cast. If it happens in underground, it will lead to life loss, property loss, mine caving, and several systems that we will be discussing in a very short way to understand how water ingress can be actually be a factor. Now, before we go to the simple details and take you through this journey, let us see what basically it comes to be as a part. So, this is the topic of this discussion, and I am M.K. Mukherjee from Department of Applied Geology from Indian School of Mines. Waterlogging systems occur everywhere where mine happens. And the idea is this, because mines have operated below the groundwater table, and the moment you cut the groundwater table and go and make an excavated space, the water will now seep in and will try to fill up that space in order to make the piezometric head balanced. So within this situation, our idea is that the mining cannot continue, but the real mining product is beneath this groundwater table. And here, one example is that this is in a tin mine in Africa, how the pumping is basically done, and we can see that the pumping is basically continuously done, and the water has been totally pumped out successfully so that the mine can be done now a bit easily. In India, this is in the Manuguru coal field, in the Singarani collieries, waterlogged systems. This is the largest barium sulfate deposit of the whole world, the Mangampet barite deposit. Severely waterlogged conditions in the mine phase, 3 or 4 pumps working continuously. In the case of underground, there is water seepage coming from the walls, from the ceiling it is dripping down, from the floor it is coming up. The whole railways are totally seeped up with water. And this is how the major water influx takes place. This is an example of Poland, and in this, it's an inflow of zinc and lead ore mine. Now this is the last example, which has led to life loss. It's in Meghalaya recently. And you can see that on December 13, 2018, at least 15 miners were buried in a rat hole mine at Kasan in Meghalaya's East Jayantia Hills after it was suddenly flooded by water ingress. So this is what exactly actually happens in all coal mines, in all metal mines. So today, the idea is that why estimation of water inflow is necessary. So now what we have to do is, before the mine opens up, or a mine is planned to be excavated, whether it's in open cast mode or in underground, we need a hydrogeological report, and we need this particular number value of how much water will actually peep inside when the whole excavated space will be open for us. So then, if it is basically an underground mine, then that dimension of space should be opened up, and we must have some value within our thumb rule so that we can calculate that value and accordingly design the pumpage system before the mine can be made into an incline, and then it can be opened through an incline. In the open cast also, we have to actually see open cast poses more dangerous problems because it is not only the groundwater. In addition to that, there will be a surface water also that will seep inside. There will be rainfall, there will be topographic river valleys that may also drain water inside the open cast. So there will be many sources which may make accumulation in the open cast systems. So there are 2 examples we will actually today study. One is in Rajgamar dip site in the Korba coal field and the Mandraigar coal fields in the Chhattisgarh. Many of our friends have actually deliberated on Mandraigar coal fields, quality of coal, then different CBM and other things. We will see how this sort of a mine can be actually in fact properly oriented, and we can understand that how water inflow should be first of all calculated, and we must come out with some values that will in fact tell us that this amount of water will be flowing within these levels, and as we go deeper inside the mine with the different levels, that much amount of water will be available inside the space, and accordingly the pumpage will be designed. If there is a power failure and 24 hours at least if the power does not operate, then what happens? The whole mine will be waterlogged and you cannot dewater it. It will be a huge loss to the system. Now, number one, mine waters inflow can cause life. Water inrushes and inflows can delay and cause the cessation of mining work together with the loss of equipment. Steady inflows into a mine water needs to be pumped out because mining cannot proceed under waterlogged conditions. Mining activities can result in the lowering of water tables, pressures in aquifers, thus threatening the supply of good quality water surrounding. Means when there is a mining, surrounding villages may have a drawdown of the water and they may not find water in their wells. The wells will all dry out. We'll see how it is. And now what to do? So we have to do things in an integrated way. We have to actually study all these parameters actively in the field through a rigorous field work, and in the study area we have to characterize all these data sets and integrate them to find out that particular value. So we take up the first case. This is the case of the Gare Palma 4x5 coal block in Mandragar, where I have worked there as a part of a consultancy project sponsored by the Monet Ispat Energy Limited. And I had been there for working continuously for the company. And here I have actually worked out this particular map that you can see. This is the part which is the study area, and we can see that this is the coal block that has been actually the study area block, and surrounding topography is very rugged, and there is a lot of topography. And there, if you can see that when I overlay this on the geological map, this is basically the one which is the Varakar formation, the major coal rich horizon. Overlying is basically the barren measures, and then the soil cover, and then the Raniganj formations are there also. What happens, the plan of this particular mine block is that it is an underground mine at present, but the upper part is actually planned to open up as an open cast. So then when they are going to plan it for an open cast, they have to calculate how much water will fall inside so that they can plan accordingly the pumpage. That was the problem. And then towards this, we will quickly see the results. So this is the blue colored part, which is in fact they need to be actually converted to the open cast. And these are and then for that reasons, if we superpose the topography, you will be able to see that this part is basically the one which is to be converted to the open cast. The red part is already in the underground situation and continuing. Later on, if you are just removing this part, you will be able to see that this open part is converted on the soil cover. That means here the overburden is quite shallow. So we don't need an underground situation there. So the company was clever enough to understand that if we make an open cast, we will be making a better productivity and output. So what they did is they have proposed for this plan and went for a hydrogeological study, and that study is actually the case that I have done. Now, let's go to the ideas. The beds are in general dipping towards very shallowly dipping, almost horizontal 5 to 10 degrees dip towards north-northeast and northeast. And one characteristic thing is that the beds are characteristically layered, but they are having compositional variations within thicknesses. So the thickness variations, and there are joint sets that in fact make the rocks vulnerable for seepage of water from the surface inside. So that is the problem. Now here you can see that joint sets. This is the surface on a plan view where they intersect, and they are the areas where water can seep inside. The rock is basically a arkose consisting of plagioclase, feldspar and quartz and minor matrix. So what happens is that during this matrix erosion and the plagioclase, feldspar getting gradually decomposed away, the passage of water day by day increases, and the groundwater flow, which is basically, if you find an open cavern inside these rocks, it is easy for an inflow to occur. So that is the idea. So we need to understand how much is basically characterize the structural systems, understand the fractural networks, and how they can make the seepage, and we have to make a balanced analysis. Now we make a geomorphological analysis to understand the general topographic with the drainage density, number of streams, bifurcation ratio, ruggedness and soil cover thickness. We measure it directly in the field, use it for the modeling, and then see the erosional pattern in this area, what actually makes the water seep inside the ground. This is the way the erosions basically taking place by the water, and they are very easily resolved away, and deep penetrations on the ground surface are made. And then this is how the water will get inside and will actually populate the mines and flood the mines inside. First thing that we actually do is to map the water table in the local area and the study area. So the simple process is that we drop the plumb line into the water table and then see its GPS and see its MSL level and also the BGL level. So both below the ground table level and the mean sea level, we try to see these heights and then develop from numerous wells throughout the study area. We actually, this is the total regional part and this block area is this much. You can see when we plot the water table, this is basically the water table's configuration. It means that the water will be actually trying to flow in this direction. It is flowing here in this direction. As you can understand, please remember that this part is going to be converted into an open cast. So you can understand that the water will be entering into the mine from the eastern side towards the west. So if the mine is open cast, the wall, total eastern wall will actually be the avenue of the seepage of the water that will get inside the mine. Plus, in the underground systems also, water is continuously flowing like this. Now in this situation, we have a petrographic study and we carry out the laboratory porosity and bulk porosity and permeability studies for the understanding the hydraulic conductivity of the water of the formations. And then we will also measure the hydraulic conductivity and water flowage as a Q discharge inside the mine directly. There is the underground situation. There are the areas where water is coming out from the ground. This is totally seeped out. Here water is directly flowing down, just like pouring out. So all these situations we calculate and we have made a value and measured the value to be this much. So this amount of water flows per centimeter square per second. Now, when we understand for an open cast, this will be the sum of all these four. Groundwater inflow, water in the surface excavations, precipitation inside the surface excavations, and stream discharge in the open cast. So the idea is that we model this area in an open cast system by making a half pit model where we consider that water is basically flowing from the wall side also and through the floor. Now this is only for the groundwater, not for the surface or rainwater at all. So this is basically, as per the Manelli and Nicoli, we have a general aspect of steady state flow that will be in fact going into this mine and filling up as a pit lake. So the pit lake will form by accumulation of groundwater from all sides from the piezometric control lines that will actually form. Now we have two zones initially as the model, that we have the pit base floor. That means you can pump off this water and then in that case the total height of the aquifer level will be just this much. So this is basically the one which is actually getting filled up over the time. And this is the no flow boundary. So here the water will actually come up and get inside this, and above this no flow zone boundary the water will always come and go from the side. So it is a horizontal movement and there is a vertical movement. So we have two different types of conductivity. One is a horizontal conductivity, another is a vertical conductivity. So these two we measure in the laboratory, and also we also make the model as a radius well and go with the mathematical modeling with this part. We don't go into the details of this modeling. Our idea is to find out the value of Q, that is the amount of discharge that is coming in both cases, Q1 and Q2. So through a detailed calculations that we actually have done, we actually arrive at these values, which is Q1 and Q2. So the Q1 and Q2 values in fact add up to form the total value of Q, which is basically the general amount of flow inside the mine just because of the groundwater. So this is the general figure. The Q1 and Q2 is basically in gallons per minute value. So the total predicted gallons per value is basically for the first 20 meters of the open cast mine, when you are going from the surface to the down, it is 24852 gallons per minute. For the next 50 meters, we will be 18,178 gallons per minute. And in the next 200 meters, although 200 meter open cast mine, I am not aware whether it exists. Maybe it is there, but if it is there, it is 15,019 gallons per minute. The idea is
a general look at this data shows that as you go deeper, the total flow value also decreases. Because the rocks become more compact inside, and then the flow value is basically decreasing in this part. So this is the part, and then we have to actually take up the total data from the different topographic drainage systems. You can see that the one drainage line goes into this particular open cast zone, which is going to be happening. So this part is basically to be modeled with respect to the water flow that will be calculated by measuring the total stream discharge for each and every streams, and that reads to 47,050,475,200 GPM. This is only surface water flow. So the mine, when it should be open cast, it should be opened up. We should take care that we must not allow this amount of water to flow from the drainage into the mine. So we should keep it at bay, and accordingly recommendations are given. So there are recommendations that indicates that we have to plan the surface excavation should be geometrically planned so as to face the flow directions of the groundwater rather than following it, so that the water will drain away naturally. Finally, we must also see that during rainfall it is expected to generate excessive sediments. So this part should be very taken care of so that we do not populate the entire haul roads and everything with sediments that may create problem for groundwater accumulations. So this is the different recommendations that we actually give it, and we calculate separately the surface water flow and the groundwater flow inside this open cast mine to understand how this is basically going to be giving us a first-hand value. Now this has been tested by Monodispath Energy, these values by a drilling hole, and it has given a fairly good agreement. We have up to maximum 18% of disagreement and similarity up to 5%. That means between 5 to 18% of error we have from this prediction. And what is the result of this particular water inflow? This is the result. The well has dried up. You can see it's a dried well in the villages. So the company has been recommended by us that they must take a CSR activity to submit and surround, and all this water that basically lost, they must be actually supplying it pure, potable and filtrated water as a drinking water to all the villagers. So this is the part of the open cast. Now come to the underground part, which is a small case, which is again in the Korba coal fields. It's Rajgamar. Rajgamar is here, and the deep side, the beds are dipping towards east. So this part is basically the study area of the block. A geological mapping. A similar study has been done in the earlier cases also, as we have done it from the geological point of view. The geomorphological parts, the landscape and the topography and the drainage lines and their parameters to find out what is the amount of water they are basically going to, what is the water budget of this area. You can see the drainage areas are basically flowing through this particular underground mines. And this is the water table. After mapping the water table by continuously taking water level data from nearly about 50-60 wells, we have made this contour, and this contour shows that how the water is. This is the north direction, and water is basically flowing, they're converging towards Rajgamar village. So if you are basically seeing this and seeing it together, then it happens like this, that north is this side, this north is this side, so Rajgamar is this side. We have to rotate this map in fact. Then we can see that all water are flowing towards this particular mine, indicating thereby that there will be a lot of water inflow inside the underground. Now see how it is actually happening. In the cases, we actually have determined the hydrogeological parameters also through the laboratory and the field tests. So there are hydraulic conductivity also determined, porosity, permeability also determined, and the general block area also has been determined, and natural seepage points also has been marked. So these natural seepage points are where the groundwater table intersects the topography. There the seepage occurs and the water comes out. It is rich in iron, so it deposits iron on the floor of the ridge and then falls on the river. So this is how the natural seepages and the rates of seepage we can calculate. Then see the erosional characteristics. Huge potholes are made because of solution of the arcosic sandstone barakars, and this, when they join in the depth, they form large areas of huge avenues of water ingress. This can create water inrush. So it is not ingress alone, it is an inrush. Suddenly a huge amount of water may flow inside and it will be flooded in no time. So if it breaks through the open space, then almost surely it will be a life loss. So this is what exactly happens. Now for this model, we have a different governing equation to model it out. It's like a tunnel. We think that it is a tunnel which is like a underground incline which goes inside, and we have the discharge rate, as per the Domenico-Schwarz equation, we actually use this governing equation for modeling this Q value, that is the discharge level. And there we predict with this equation that with respect to this 50, 10, 50, 90, 130 and then up to 330 meters of depth for a gallery whose height is 2.5 meter, width is 4 meter and length is 1000 meter space, open excavation. How much water will be accumulating? For the first 10 meter, we will have this much of 19,834 gallons per minute, and this gradually decreases up to 4397 as 330 meter. Simply because the rocks are more compact and there is no porosity inside. So that's why it decreases with depth. So with this has also been tested by the Southeastern Coalfields Limited by their drilling, and this also gives almost 6 to 7% error and matches well with the data sets. So this is how the two things are basically, in a case of an open cast and in an underground, we can predict a water inflow. And there are, naturally, then we have some whole list of recommendations that they must actually do this from the hydrogeological studies and accordingly make it. Thank you very much. And this is what exactly I have to say. Any questions?
Thank you, Professor Mrinal Kanti Mukherjee ji, for having given the insight on the water ingress in open cast as well as in underground mines. Now we can have a couple of clarifications on this keynote talk. So, I have one clarification.
Yes, sir, please.
Naiveli lignite mine in Kadalur district of Tamil Nadu,
Yes, sir.
that is also an open cast mine.
Yes, sir.
There also they are facing the water problem.
Yes, sir.
So can this particular
Yes.
model can be applied to
Yes,
that mine?
Yes, sir. It should be seen there.
Yeah.
Accordingly, we have to see the other parameters also, but the governing equations remains almost same. But there are certain points of hydraulic conductivity that we have to change it there accordingly, because geology is not a thumb rule.
Yeah.
Every area has to be having a different fingerprint. So accordingly, the parameters has to be adjusted. Otherwise, the general modeling can be also done by this method only.
Thank you very
That's
much.
all. Thank you, sir.
Thank you. So this is the last, Dr. Rajiv Nigam.
Yes, sir. Yes, sir, please. Yes, sir. Yes, sir. No, sir. Water will not return anymore, because already the mine has been done. If the mine is filled back, then possibly we can think of water getting reclaimed again, but not to that level as original. It is not reversible, sir. Groundwater table once gets depleted because of mining, it is not reversible. Now, if we close the mine, fill with sand, fill with all boulder materials and totally lock up the space, possibly to some extent it can be reclaimed, but not to that level, sir. Yes. Now they are. Yes, sir. This is a tremendous, valuable question you have asked. I mean, this is a matter of, I must not say it, but this is exactly the reason why private mining, many coal blocks are stopped, many private mining is also stopped, many sort of CSR activities are reviewed continuously to say that whether they are monitoring, and this. We have to understand that this is not with all companies, but in many cases it happens when the mining people go away, so it remains like a pit-filled lake, and the whole open cast, if it is, then it will be a pit-filled lake. Still, open cast is still something better, at least you have some accumulated natural water, but underground is even dangerous. It is. Yes. Yes. That is the thing. It's very difficult, sir. Thank you, sir.
There one.
Yes.
Thank you. First of all, let me thank you, sir, that he has did very nicely and in understandable manner actually. I have a question that while solving this water ingress problem in open cast and underground minings, I want to ask that what are the common problems you have faced or you have studied, and what are the most challenging problem and how you have obtained solution for that?
Specifically, if you ask me what my field experience is, I did not face much problem in the field because the company has given permission, but the people, I had a bit hostility from them because they are thinking that our water is basically getting lost. So in fact, I need to convince them that I am working for that only. Although I was not working for that, I was working for, in fact, predicting how much water will enter into the mine and would like to aid the company. The idea was that, in fact, that way I carried out the work. But the most difficult thing was to understand the anisotropic variability of the permeability. The hydraulic conductivity is so anisotropic and arcosic sandstones are not same everywhere. Although there is a continuous lithoform, but we can see that hydraulic conductivity varies from one point to the other. So we actually had made a hydraulic conductivity contouring also. That I have not shown here. So that is basically that we submitted in the report. But the idea is the hydraulic conductivity point was so variable that we need to see and try to maximize this variance within a particular limit and take and choose that particular right value which could have satisfied all the areas in a proper way. So this was the major challenge to, in fact, bring out the KH1 and KH2. There is the hydraulic conductivity on horizontal way and the hydraulic conductivity in the vertical way. So this, we have carried out blocks of rocks inside the laboratory, and in our engineering geology lab, we have actually made this permeability test vertical and horizontal by putting jacks of water that is forcefully injected inside the rock under a pressure, and next morning we see how much has been wetted inside. So that gives the permeability as the horizontality. So this way we could actually make. And next horizontal permeability we can see directly in the mine because water is coming from the wells and pouring out. So that vertical wall is pouring out horizontal flow. So this we directly measured in the field. So those we matched totally and then converged into a particular value of hydraulic conductivity. Otherwise there was not much administrative problem, and technically this hydraulic conductivity contouring requires a lot of very carefully deliberated strata. Otherwise we will come into a wrong interpretation. Because coming to that exact value is very challenging.
To say hydraulic conductivity is the continuous flow of water, or it is stream of that water chain you are referring to?
No.
Is it so?
No. Hydraulic conductivity is actually a distance. How much water flows in unit distance in unit time. So this is called hydraulic conductivity. And the amount of discharge that comes out within a cross-sectional area is basically the Q. So discharge and conductivity has a relationship. So we actually do it from the Darcy's equation, and here we have used a modified Darcy's equation to understand the hydraulic conductivity and the discharge. So we do the hydraulic conductivity also, we do the discharge also, and then we also have a one-to-one and then plot it in a graph to find out that correlation. If it gives exact Darcy's law, then it will exactly fit that equation. Otherwise, it will give a modified value. So we have made that value.
Okay, thanks a lot.
Thank you, sir.
You have explained very nicely. I hope everybody is benefited with this your explanation. Thank you very much.
Thank you very much, sir. You please come here. Sir, please come here. You are. Thank you very much, sir, for your excellent keynote address. There is an announcement to be made by the organizers.
Good evening, everybody. It is to announce that we have arranged dinner from 8 to 9:30 p.m. here. So please stay back, and or if you want to freshen up after the session is over, you can go and come back please by 8 p.m. We may start even earlier, but please be here for dinner. Okay, thank you.
Thank you, sir. So this
thank
is the
you, thank you, Professor Rajan.
So this is the last session. We are running late by 1 hour, and we have to make up the time. And now I invite R.H. Chauhan to give your presentation, Geological Surprises and Geophysical Constraints in Concealed Coal Exploration Area, a case study from Wardha Valley Coalfield, Central India.
Very good afternoon to and very good evening to all the STEAM participants, dignitaries on the dais and off the dais. And it is very late. I hope so you are having some patience to listen to my topic, a very interesting topics that have worked out in our very coal field. And my association with coal exploration is just 4 years old. And whatever the knowledge I have gained under the guidance of all the seniors, especially Mughal sir, who has worked in the nearly 25 years, this is the output of his work and our observations in the Vardha Valley coal field. Sir, as you know, the coal affordability and its probability is a very paramount important that's play very paramount importance in energy sector. That's why coal is very important. And GSI is taking the challenges right from the beginning since in last 50 years to carry out the exploration projects in on the pan-India basis, whether it's a Vardha Valley coal field or Narmada or the Damodar Valley coal field, or whatever may be coal fields. We are ready to take challenges and whatever the problems we are facing, without any facing problems, we are giving a sustainable resources to our countries. So to begin with, my name is Ashtapal Chauhan, Director, and I am also a training institute director, and beyond that I am looking after all the coal exploration projects. As I said, my association with the coal projects are just 4 years old, and the topic of this presentation is geological surfaces and geophysical constraint in the concealed coal exploration area. Why it is concealed, I will just let you know. And it is a case study of the Vardha Valley coal field, and particularly I am talking about the Lathi Kesurli block or area. The area means that is the G4 exploration work carried out by GSI in the Vardha Valley coal field in the Lathi Kesurli area. So to begin with, I will just take you to my field site, my study area. This area can be approached from the Nagpur, that is of at a distance of 130 kilometers to the south of the Nagpur, and Vani that falls in the jurisdiction of the Yavatmal district. From the regional geology of the Vardha Valley coal field, we can say that it is Vardha Valley coal field is a continuity, northwestern continuity of the Godavari Valley coal field, and with having a similar setup. But however, little is known about the coal measure of the Vardha Valley coal fields because it is overlain by Kampti formation, Motor formation, and Deccan basalts. As from this Vardha Valley coal field, we can see the northwestern continuity. Northwestern area is flanked by the metamorphic rock and then followed by the Vindhyans. Vindhyans are flanking to the northwest and to the northeast areas. Then in the centers, we have a Talchi inlier. And whatever the projects, whatever these blocks you are seeing is nothing but the explored block by the GSIs. So the unexplored area that is left by the GSI, we have carried out the G4 explorations in this area, and this is we called as a Lathi Kesurli area. So we will see what things we have been getting, what are the adversity we are getting during the explorations, and what are the surprises we are getting in these concealed coal deposits. First of all, I would like to say that this is in 1994, Mr. Kazmi and others have just carried out this work and they have mapped this as a Kampti formations. But to our surprise, when we are doing the surface mapping, we found that with some surface data and subsurface data, we said that it is a Motor formation. That is the first things we have we have pointed out. Now, let me just take you to what is the general structure of the Vardha Valley coal field. And Vardha Valley coal field, as you know, it is a broad antiformal structures. To the west, it is bounded by the Vardha Valley coal field, and the center part, it is occupied by the Bandar coal field, and further to the east, it is Umred coal field. The general strike of the coal beds here is 130 to 155, that is northwest southeast, with dipping towards 12 to 15 degree toward the southwest. This is important. And each sub-basins is a faulted basin, half-governed basins, and the beds we are occupied on the northeastern sides, dips toward the northeast sides, and the beds which occupy the southwest dip toward the southwest directions. This is a very brief account of the regional structure of the Vardha Valley coal field. Now I will take you to the my block, that is Lathik-Esurli area. As I said, it is previously mapped as a Kamti formation, and based on some surface mapping, so the sedimentary package we are getting on the subsurface map, on the surface mapping, we say that it is Motor formation. Next slides, I will show you the why we called it a Motor formation. Some field criteria I will show you. And now we decided that it is a Motor formation. So according to my previous sentence, I said that it is northwest southwest strike direction. So I expected with a deep amount of 8 to 12 degree. So I expected that to the southwest I won't get any coal bed. If I will get the regional coal bed Barakar formations, that is at a greater depth. But once I said it is a Motor formation, so I can conclude that the Kamti formations may be washout or may be erosion, and whatever we are at the surface in the form of paleo horizons filled with vertical burrows of a medium to sine grains that indicate that it is a lower Motor formation. That means Kamti formations is not exposed here. This is the first thing we have come across. And one more thing that we are envisaged that top of the coal seams will intersect it at shallow depth of 300 to 350 meter based on the observations that the paleosol horizon in Lathik-Esurli area. So we drilled the first borehole here, WPR1. Okay, expecting that we may get a coal seam at a depth of 300 to 350 meter, but it is not so. Why? I will tell you. Then after drilling this point WPR1, and we are not intersecting any coal seams at the depth of as expected, anticipated at the 300 to 350 meters, and this borehole was goes at a depth of 457 meters. But later on, we just shifted our coal exploration project to the east of this block, and this is actually, this borehole is actually WLK1, that is Lathik-Esurli area borehole number 1. This, we have taken this anticipated depth based on the CMPDA work of one borehole that is here. So they have intersected coal seam at a depth of 459. So we have also anticipated that the borehole here, WLK1, we will intersect the coal seam at a depth of nearly 500 meter approximately. But to our surprise, the WLK1, the coal seam has intersected at a depth of 680 meter with a Motor Borakar formation of 310 meters. Now, similar geological adversity we have expected here in WLK. Then we have just explorations toward the deep directions of the WLK1 at a distance of nearly say 2000 meters. Here in WLK2, we did not did not intersect any coal seams at a depth of another 457 meter or 460s. So we abandoned that borehole as we do not intersect the coal seam. Then we tried another borehole in the vicinity at a distance of 10 meter. Then again we are failed to intersect the coal seam at a depth of nearly 500 meters. But later on we are just shifted we have failed to intersect coal seam WLK2 and 2A. But again, at a distance of say 10 meters, adjacent to the previous borehole, we have intersected coal seams at a depth of nearly 700 meters. As we are expected, it is 500, then it has gone to 700 meters. That again, this is unexpected results had been happened. So, and all these boreholes, WPR1, that is in the poorer area, and WPR2A and 2A, they are close at nearly from 457 to nearly 500 meters. So, then next, we have just changed our idea, and we thought we have just gone to the northwestern boundary of this block, where we have some borehole data of CMPDI, and that was closed on the 496. So we have assumed that that is actually the part of the we assume that that will be the lower Motor formation or just upper part of the Barakar formation contact. Based on this, we expected that we may get regional coal seam at a depth of nearly 550, but this is not the so. Then again, our WLK3 has failed, has not intersected any regional Barakar coal seam. Again, we applied for the same. Then we again 10 meters to adjacence, we drill again WLK3A. In that, we have intersected the coal seam at a depth of 810 meters. Then we have just shift our planning of explorations to further to the southeastern part of this previous boreholes to cover all this 80 square kilometer of the area. Here in WLK4, again up to 900 meters, we have not intersected any regional coal seam. So we have interpreted that this part may be a part of the depot center of the basins. So these all boreholes indicate that they have some signatures, they have some relations, overlapping relations with gravity map, Bravo gravity map, that I will explain in the next slides. So these are the common features of the Motor formations, that the vertical burrows that filled with brick red color sandstones at the Kesurli. Then this is very near to our study area. It is falls in our study area, and then ferrunized red color that sandstones and grey color medium sandstones, massive sandstones. All these are the part of the Motor formations. And to appreciate this work, I have drawn one section line from C to D and from A to B, and from C to D. C means from WLK1 to WLK2B. This actually the intersection of the coal that's shown in the sections. And this is actually the Motor Barakar formations contact. Now this table, if you see, the Motor Barakar contact has a 310 meter, 680 meter, and I'm sorry, this is a 310 meter and 456 in WLK1 and WLK2B. And the regional Barakar coal seams will be intersected at 680 and 806 meters respectively. And the cumulative of the thickness is nearly 20 meters. As we go further to show these sections, we have a WLK3 and MWM4, that is the reference bowl. We have not intersected any coal seams in WLK3. and we got all the motor formation that never be expected of so much thickness because of the because of the sin depositional, sin tectonic activity, the disturbances in the basins. Again, sections along the borehole 3A and 3-4 and 4A, where I said that we have not intersected any regional Barakar coal seam, but we have marked some contact of motor formation 647, up to 647. So we can say that the motor formation thicknesses goes on increasing and increasing at the depth, maybe because of the sin tectonic disturbances. Okay. And if you correlate all the seams, we have seen that motor Barakar formations at 310, then 456, then 570 and 657. This indicate that the maybe some fault at the depth that may be around, there may be a listic fault, and the motor formation itself get faulted during the deposition of sediments. So last, this is geophysical constraints. What we observe after overlapping our area in the geophysical Bauer gravity map, what we found that this WLK1 where we have intersected coal, WLK2B and WLK3A, these all we have intersected a regional Barakar coal seams within the limit of, that is a Bauer gravity anomaly, within the limit of -45 to 50. And as we move from the -50 Bauer anomaly, we may entering in the depot center of the basins. So that is the conclusion we can draw from these geophysical constraints. And depositional milieu of Varda Valley coalfield, we thought that the source may be at the another sub-basins, that is lies in the Bhatali and Ekarjuna area, and our area which is Lathika Surya, the south of these sub-basins. So here some oxidized zones we have observed. So we thought that the southern part of that is in the Pural or Lathika Surya may be exposed a shallow water, and that is why we are getting oxidized zone at a very low level as compared to the northern part of the Bhatali and the Ekarjuna blocks. So there take-away message to begin with. Author's opinion that the large-scale erosion of the overlying Kamte group of rock exposes the lower motor formations as a virgin tract of the unexplored area. And the borehole WPR1 and WLK4, which are not intersected regional Barakal core seams up to a depth of 470 and 900 respectively, are actually the unexpected thick sedimentary argillous package and formation complexity and thin tectonic disturbances we can infer. So, in addition to that, we are getting problems in identify the motor Barakar formations contact and is differ from person to person. Furthermore, we can say that any geophysical exploration activity, if we carry down the features, so from this we can infer that we can restrict our coal exploration project between -45 to 50, and beyond that it is not advisable to carry out any exploration project in the Varda Valley coal fields. That's all about, ladies and gentlemen. If any questions, I am most welcome, and thanks for your patience hearing. Thank you so much.
Thank you, Dr. Chauhan, for your nice presentation. And we can have one or two clarifications on this particular presentation.
No questions? Okay. Thank you very much.
Thank you, sir.
Chauhan Saab. We call the next presentation. Just. Yes, Dr. Sandeep, you have.
It's very interesting presentation. My simple query is like your whole confusion and your surprises of geological nature is based on the premises that what you observed, the outcrop was a
Not parameter, it's a motor formation.
motor formation. That's the equivalent. Like, okay, I'm not a coal specialist, you are a coal specialist, but I understand little stratigraphy. But is it possible that it is actually not a motor formation what you are observing? Then the whole premises is actually, this whole conjecture actually changes. The possibility of not being a motor formation is quite high. What is your take on that?
Sir, we have done WPR1 in Purar block. So much argillaceous package of clay stone, mudstone and sandstone and Hentuli sequence you won't get in the other formations. That is the only criteria. And their argillaceous is more as compared to your arenaceous material. And that is the only criteria we have, that is. As such, we won't get it, sir. It is
no
a finger.
other sedimentary granulometric analysis, no other more
No
fundamental
such data is
characters?
available. From the drilling data, what we are expecting, sir. We will logging, and based on our logging, I said that it is argillaceous material, more argillaceous than arenaceous. If it is more arenaceous, we can say, yes, we are the part of the Barakar formation. But it is not so, that's why we are saying the motor formation. And some surface features also we are just, the vertical burrows and the paleo soils, all these features mapped during the sedimentary mapping in 2018. This all means we are very much sure that it is motor formations.
So that is the premises. Are more argillaceous, less argillaceous, more silica?
Exactly, sir. Exactly, sir.
Okay, thank you.
Okay, thank you.
Thank you, sir.
For giving the question and also the answer. Thank you. Okay, we now invite for the next presentation S. Gupta Meena, Karnam Chandra Rao and Vijay Mughal. Petrographic and geochemical characterization of coal from
important source for rare earth elements. So, exploration and exploitation of coal is very much important. So, the coal exploitation depends mainly on its chemical is very much essential, and apart from its economic concern, coal is an also important indicator for paleoclimate, paleo-environment and geodynamic studies due to its intrinsic details and long-term records. So, these details are interpreted through the study of its botanical, geochemical, mineralogical, palynological and petrological compositions. So, on this basis, an attempt has been made to study the coal from the Lathi-Kesurli area, Wardha Valley coal field, to study the petrographic and geochemical characteristics. This is the geological map of Wardha Valley coal field. इसका ये पॉइंटर this is the geological map of Wardha Valley coal field. The Wardha Valley coal field is the northwestern continuation of Godavari Valley coal field, and it lies in the Yavatmal and Chandrapur district of Maharashtra and is one of the potential areas for coal mining in central and western part of the India. Our Lathi-Kesurli area forms the part of the western limb of plunging anticline in the southwestern part of the Wardha Valley coal field. Here this is our Lathi-Kesurli area. Much has been told by Chavan sir regarding its borehole details and geology, so I will not go into detail of that. This is the geologic outcrop map of the area. So most of the area is covered by soil. A few outcrops of sandstone and mudstone are present along the Nala section, and these are the borehole locations from where we have collected samples for petrographic and geochemical characterization. This is the graphical lithologue of the boreholes, and from out of 4 boreholes, 3 boreholes we have intersected coal, and the depth ranges from 681.89 meters to 831.85 meters for the regional composite Barakar coal seam, and from 837 meters to 846.23 meters for the local coal seam. And these are the details of the individual coal and lignite seams intersected in these boreholes. And these are some of the core photographs which are intersected in our boreholes. This is a sandstone, poorly sorted sandstone from Barakar formation. This is again the fine grained sandstone with thin lamellis from Barakar formation. And this is the coal and carp shell sequence from the coal seam of all the 3 boreholes. And this is the mudstone, this is the sandstone from the motor formation of the borehole. And these are the coal intersected in 3 boreholes. This is intersected in WLK1, this is WLK2, and this is WLK3. So going into the subject, actually it is very initial work. Lot has to be done in this because a lot of geochemical analysis has to be carried out. We don't have such facilities right now, but we will try to do our best. So coal petrography, why it is so important? Coal petrography is the study of coal samples under microscope to provide the description of macerails and maceral group mineral matters, which in turn establishes its maturity level or rank of the coal. Because rank of the coal is very important for its use in any of the sectors. So we have collected 7 number of coal samples to study their petrographic details. And when we see the coal samples in hand, so we see bright to moderately bright in appearance, and at places it looks moderately dull due to fusion or Durand bands. Few pemeroidal pyrites are also observed in the hand specimen as well as under the microscope. The maceral analysis reveals a predominance of vitrinite, which is ranging from 47 to 74% over inertinite and liptinite. The mineralogical analysis shows that these coals are characterized by high mineral matter dominated by silicate mineral. The main silicate mineral is being quartz, iron oxide, and non-oxidized pyrite. And this is the photograph of the coal section. Here you can see different kind of bands, and in this we can see vitrine spots along with the fusion bands. And this is the result of maceral analysis. From this table we can see the dominating maceral is vitrinite, which is followed by inertinite and liptinite. The maceral analysis studied coal samples are all high in mineral matter with varying amounts of vitrinite, inertinite, and liptinite. The vitrinite liptectins indicate that the rank of the coal is high volatile bituminous, while the maceral textures suggest it is in transition from subbituminous to high volatile C or B bituminous type. Vitrinite group is represented by coletellinite and few colodetrinite bands and vitrodetrinite bodies. Cleats are visible in both the coletellinite and colodetrinite bands. Some transitional phases from vitrinite to semifusionites are also visible. Inertinite group is represented by semifusinite and fusinite, which are present mainly both as bands and as discrete bodies, along with macrinite, secretinite, and metrodetrinite. Unicellular and multicellular fusinites are also present. Liptinite group is represented by sportinite, cutinite, exudetrinite, and fluoritinite. Now going into the geochemistry of the coal. So for geochemistry, we have done proximate analysis and RE analysis by ICP-MS analysis. From proximate analysis, we found that ash and moisture content of the coal samples determined through band by band proximate analysis along with the GCV of overall sample are taken into consideration for description of quality of coal seams. So the result indicates that overall sample includes coal sections having ash plus moisture content up to 65% and dirt bands with maximum thickness of 30 centimeter. Proximate analysis indicate low moisture content, moderate fixed carbon content is range between 47 to 74.91%. The coal samples show high ash content. The average GCV value is 5025 kilocalories and grade ranging from G4 to G14 categories. This is the table showing the GCV analysis of coal intersected in the boreholes. So RE geochemistry. So we have taken total of 12 samples of coal and associated carbonaceous shale for their RE analysis. So the total RE of varies from 81 ppm to 277 ppm, whereas in carbonaceous shale, the values of RE varies between 155 to 243 ppm. This is the chondrite normalized RE pattern in coal core samples. Here from this pattern, we can see that all the samples are showing the negative europium anomaly. So in chondrite normalized plot, negative europium anomaly is seen for all the 12 samples. The negative anomaly of the sample indicating that the source region is of felsic composition with a depleted EU anomaly due to fractional crystallization or feldspar or partial melting. As the earlier presenter told that the provenance for the sediment from the Lathi-Kesurli area is mainly the granitic gneisses, Proterozoic and granitic gneisses present in that area. The EU mobility during coal formation is the another possible explanation for the negative anomaly. So, why it is so? Because strongly reducing environment with low temperature favors the mobility of EU during coal formation. So, we are saying that EU mobility during coal formation is the another possible explanation. The high ratio between light rare earth element and heavy rare earth element for all the 12 samples together with negative EU anomaly also indicate a post-Archean granitic source rock for the detritus of the rocks of the area. So going into the conclusion, the regional composite coal seam encountered in Lathi-Kesurli area is clean and free from dirt bands except in the borehole number WLK1. The petrographic studies revealed that coal from the Lathi-Kesurli area is vitrinite dominated coal with subordinate amount of inertinite and liptinite. In terms of coal rank, the coal sample of the study area are placed into medium rank subbituminous B-type borderline C-type coal. Mineralogical analysis shows that these coals are characterized by high mineral matter dominated by silicate minerals, iron oxide and oxidized and non-oxidized pyrite. The GCV analysis for intersected coal seam indicated that the coal grade is from G4 to G14 grades, G14 level. The negative anomaly, the negative europium anomaly may be due to the EU mobility during core formation, suggesting strongly reducing environment with low temperature. So this is our conclusion on the basis of limited analysis. Now we have to do more analysis like whole rock analysis as well as trace element analysis. So we can go into much details of the sedimentary environment that was predominating during the formation of coal in the Lathi-Kesurli area. Thank you so much. I am thankful to DGGSI and DDGSU Maharashtra, and I am also thankful to Mughal sir because he guided me a lot in this work and is in this project. So thank you very much.
Thank you, Dr. Meena Gupta, for your nice presentation. You have completed within the time. Now we can have one or two questions on this particular presentation. Yeah.
Yes, ma'am. Thank you, ma'am.
Very nice, straightforward conclusion. My only thinking is this, that you did the rare earth element analysis and you normalized it with
Chondrite
chondrites.
normalized. Actually, madam, we have also did past normalization.
Yeah, I just
yes,
wanted
we
to
did
ask
that,
that.
madam. And in that we are having positive EU anomaly. So,
Yeah, but then you could have...
in some samples we are having positive EU anomaly. But I have not shown it because a lot of chemical analysis has yet to become for remaining samples. So that's why I have not presented that analysis, madam.
Yeah, but then I personally think that if you do it with PAS, I mean with American shale composite or PAS, then it would give you a different picture altogether.
Definitely, madam, definitely. Because here we are getting negative, in that we are getting positive anomaly. So picture is totally different. Yeah. But for that support, we need another analysis. So we are in that frame. So in future we are doing the other analysis so that we can conclude more confidently for that area.
Yeah, but I don't think then the provenance would be coming from the igneous and metamorphic source. It would be more coming from the sedimentary source.
Yeah, definitely, madam.
Thank you.
Thank you,
congratulations. Yeah.
Thank you.
We now invite the next presentation, Mohammad Merazuddin Khan. Please come up for presentation of concept-oriented coal exploration through high-resolution sedimentary fault analysis. Your time starts now.
A very good evening to all the dignitaries on the dais, and my friends. Myself, Merazuddin Khan, working as a senior geologist in Geological Survey of India. As you can see, my topic of presentation is concept-oriented coal exploration through sedimentary fault analysis. Already a lot has been talked by my friends about the coal exploration part. So I will directly go on my topic. If we talk about the coal exploration, traditionally it was believed that the coal-bearing strata are generally devoid of any coal seam near to the basin margin due to the presence of basin bonding faults. But this is actually not true. So what we have done, that we have analyzed the surface and subsurface data of two well-known basins of central India, and then we came to the conclusion that actually the faults which are aligned at an angle to the basin bonding faults, they have actually participated in the basin initiation, and that faults actually changed the entire scenario. So quickly I will go to the next slide. So this is well-known cartoon to all of you. So the Indian silt was basically made up of a few Archean cratons, CBM cratons, Bastar, we have Dharwad cratons here, and the Buldenkhand craton, and their proterozoic outgrowths. So if you see the location of the Gondwana basins, they're actually located either very close to these cratons, or at the junction between these two cratons, or at the contact of the cratons with the proterozoic mobile belts. So now if you see the disposition of the Gondwana basins, this is again known to all of you, but where I want to draw your attention is that these Gondwana basins were roughly aligned in two parallel directions. If you see, this is almost east, northeast, west, southwest direction, and is defined by the Damodar Valley Basin, Son Valley Basin, Narmada Valley Basin, and there is another direction which is west, northwest, east, southwest, which is defined by Paranita Godavari Valley Basin and then Mahanadi Valley Basin. Now if you see, all the Gondwana basins were actually bounded by the number of crustal scale shear zone or faults. Actually these faults were participated in the initiation and evolution of the basin. So initially it was thought that the Gondwana basin were originated as, this is traditional concept, tectonically sagged basin model, then followed by the failed rift basin model, and the most latest is the pull apart basin model, where it was stated in this model that all these basins were originated due to a simultaneous east-west extension resulted in opening of all these basins. But in all these basins, the concept that was considered is that these faults which are presently defining the basin boundary were actually participated in the initiation of the basin. This is where we have done our study. Now, we have carried out this study in two major basins. One is the Tatapani-Ramkola basin, part of Son Valley basin. Another is the Satpura basin. Already a lot has been talked about the Satpura basin geology and structure by my friends. So, yeah. So, if you're talking about the fault, because they play a vital role in any basin evolution. In case of, if you're talking about the Gondwana basins, the scene sedimentary faults plays actual role. So, the scene sedimentary faults we need to understand if you are carrying out any exploration or we are carrying out any work in any basin, in Gondwana basin. Now, these scene sedimentary faults in the rock records were actually documented by the abrupt thickening of scene tectonically deposited beds, slumping of sediments, what we call the penny-contemporaneous deformation structures, and since the coal seams are the marker horizon for the Gondwana basins, so splitting of coal seams, deterioration in coal quality, thickening of the interseam coal parting. So it is important before doing the things, it is important to understand the nature of the scene sedimentary faults that were participated in the basin evolution and not the faults which are presently defining the basin boundary. So the first study area, Tatapani-Ramkola basin. So I will quickly go through the geology part. The Precambrian basement rocks defines the basement over which these Gondwana sediments of Talchir, Barakar, then Barren Major, then Raniganj were deposited. On all these lower Gondwana basins, if you can see, they were deposited along the peripheral parts only. And the central part and the entire western part has been covered by the younger Gondwana sediments. The basin on the north was defined by a set of faults which are actually parallel to the Son-Narmada South fault. And the northern part of the basin was defined by a shear zone, which is Tatapani shear zone. Now, if you see, the basin was actually controlled by a roughly three directionally oriented set of scene sedimentary faults, either east, northeast, west, southwest trending, or the north, northwest, south, east trending, and there is a minor fault which is northeast, southwest trending. And if you see the basin profile, what it says that the basin was actually originated, the basin was actually originated as two separate sub-basins, separated by a basinal high. So what we have done is that we have analyzed the data in two different directions. We have analyzed the data parallel to these basin bonding faults and across these basin bonding faults. So this is the data which section which is parallel to the basin bonding faults. And now if you can see that the stratigraphy starts with the Talchir formation, then we have the thick Barakar formation, and the lower part of the Barakar formation has thick development of coal seams, whereas the upper part is defined by a conglomerate sequence, which has got a tectonic significance. So if you see this section, which is actually parallel to the basin bonding faults, so we are getting the coal seams, we are roughly 3 numbers in the eastern part, they are gradually splitting to a number of coal sections. And parallelly, this interseam parting thickness was also increasing. And the coal quality, if you can say this is the ash plus moisture diagram, it is also deteriorating towards the west. Now what does this indicate? This indicates the presence of a scene sedimentary fault towards this part of the basin, towards the western part of the basin, which fault is actually not parallel with the basin bonding faults. It's actually across the basin bonding fault. So if you see the upper part, there is no basinal subsidence. The conglomerate has been ubiquitously developed over the entire basin. Now if you see the section which is actually perpendicular to the basin bonding faults, there is no splitting of the coal seams, almost equal development of the coal seams, but see the upper part of the Barakar formation. These conglomerate units were getting thickened towards the basin bonding fault. See the conglomerate thickness which is increasing towards the basin bonding fault. What does this indicate? This indicates that this basin bonding fault was actually activated at a much later stage. not at the time of the initiation of the basin. So this is the famous conglomerate from the Tatapani Ramkola basin. And this is the evidence of the later reactivation of Tatapani fault. This is the break-seated zone. So from there, what we have seen that the basin bonding faults, which are actually defining the basin boundary at the present, they were activated at a much later stage. And the seen sedimentary faults, which are actually covered by the younger sediments, were actually participated in the basin evolution. So the next study area is Satpura Basin. Much of the geology and structure already been talked by my friends. So I will just quickly go through it. The basin was defined by, again, a set of faults which is parallel to the Sonamara South Fault, and in the south by Tapti North Fault. There is another fault. This fault, which has an eastern divergence, which is actually occurring at a low angle to these basin bonding faults. See the basin profile. It is a typical half-graben basin, with the sedimentary strata deepening towards one of the major basin bonding faults. So the sedimentary beds are actually now, presently, they are dipping towards north. We have the Precambrian basements here, and then successively younger sediments going towards the north. So the basin is uniformly or monoclinally dipping towards north. So what we have studied the Tajir formation. And luckily, we are lucky enough that we have got a slump fold here. And these slump folds, which is actually associated with the seen sedimentary deformation, gives us the clue about the initiation of the basin. See, we have mapped the slump folds. See, we have mapped from one to to all the different directions, and there are different sets of folds. And in overall, if I can say that the folds have a southwestern divergence. So we have broad opening type of fold in the eastern part, which is the distal part basically. Then we have upright folds. Then the fold vergence were getting towards southwesternly as we are moving from east to west. So fold data like fold axis, axial planes, thrust planes were analyzed to determine the paleoslope direction, and fold geometry were analyzed to determine the paleoslope direction. So what we have concluded that the basin was actually tilted towards west and not towards the north, which is the present case, which we are presently seeing the basin. So, and now the basin was defined presently by these two sets of faults, but they were not actually participated in the basin initiation. The cross faults which are occurring at low angle, this actually triggered the slumping. That means this fault was initially activated during the basin evolution and not these faults. Later on, these faults activated and the basin get tilted towards north. So presently we are seeing that the beds were dipping towards north and not towards west. So here is the conclusion. The basin configuration needs to be understood through thorough analysis of seen sedimentary faults, which are actually now covered by the younger sediments. The faults defining the present basin boundary may not involve in the basin initiation, what we have seen in two basins. The basin bonding faults were activated at a much later stage, and they have covered the entire lower Gondwana sequence. Areas closer to such basins bonding faults may be targeted for coal seams. Thank you all.
Yeah, thank you, Mirazuddin Khan, for your nice and excellent presentation. And this presentation is open for discussion now. Yeah. Dr. Sarolkar, sir.
One very simple question.
Yes, sir. Please.
With all your analysis, where do you put the Tatapani geothermal field in relation with the Gondwana basin?
So it's related with the Tatapani shear zone only, which has activated at
Yes, that it is related with the Tatapani shear zone, that I know. But that exactly what I am saying, whether the Tatapani shear zone is previous, afterwards.
No, it's afterward the initiation of the basin. It starts from the upper part of the Barakar formation.
So you mean to say that the geothermal field is after development?
It may not the case maybe. It may got reactivated again at the upper part of the Barakar formation.
No, I think
it may get, yes, sir.
what personally I feel that your analysis as far as what we can say, the coal field is there, it's good.
Yes, sir.
But you have to look into interrelationship of the Gondwana basin and the Tatapani fault, where these particular hot springs are coming up.
Okay, sir.
So, and that will be much useful in knowing the genesis of the field, hot springs also.
Okay, sir. Sure, sir. Thank you, sir. Dr. Peters. Sir.
Do you have any paleocurrent directions to back up your, besides the structural?
Yes, sir. We have. We have the paleocurrent in the conglomerates, which are actually going towards north.
You have the paleocurrents going to the north?
We have paleocurrent in the Barakar formation also. Before the initiation of these later faults, where the paleocurrent was towards the west. So there is a shift in paleocurrent direction from west to north. Similar is the case
shift
for...
in paleocurrent direction?
Yes, sir.
See, most of the paleocurrents that we had mapped way back in the 80s, they all were basically northwesterly.
No, that was true for, I think, sir, upper Gondwana.
I'm talking only about Satpura.
Okay.
Not only for upper Gondwana, even for lower Gondwanas. Yeah. So if you could club your structural
with paleocurrent data.
With the paleocurrent this thing, you would get a better, a more meaningful conclusion, right?
Okay, sir.
Thank you.
Thank you, sir.
Last.
Miraj, I have one question regarding Satpura Gondwana basin.
Yes, sir.
You are talking about the western part of the Satpura basin, and the first presentation from Bamanwada sector, it has been proved by the drilling data that the basinal boundary faults are being parallel to the basinal boundary faults. So whether it is applicable to entire Satpura Gondwana basin or part of the western part of the Satpura Gondwana basin.
Sir, we have done this study in the eastern part rather, but the fault sets that you are saying that may be, that needs to be identified whether these faults are syn sedimentary fault or post depositional fault.
Because it's contradictory as far as eastern part is concerned and western part is concerned. If
Yes,
you are saying that it is deeping towards west instead of north.
Yes, sir.
But it is totally applicable in the eastern part, as
Yes.
it is presently done work by earlier workers, shown that it is dipping towards north only. That's why we are not getting coal at shallower depth towards northern direction. So it is the exploration data we have. Since we are doing work from last 15 to 20 years, so that is the established data in the eastern part. However, in the western part, we have not gone up to that level of exploration. So please check all this data for entire Satpura Gondwana basin. That's my suggestion.
So far what we have done the Talchir and through the exploration data, it is well correlated. As we have said, that the basin in the eastern parts was tilting towards west. And we have done the Talchir analysis in the eastern part of the basin itself. So it is correlating, surface and subsurface data is correlating basically. So it may be the case for entire basin. It may be. There are a set of faults which are northwest, southwest directed that initiated all these Pench, Kanan and Tawa basins. That may happen. But for this, we need to analyze those faults, whether these are syn sedimentary faults or post-depositional faults. That need to be identified, sir.
Thank you. Thank you, sir.
We can have the discussion during the dinner time.
Yes.
Thank you,
Sir.
Mr. Khan.
Thank you, everyone.
Yeah. And we move on to the last presentation of this day as well as this technical session. I invite Hemant Kumar Singh. And he is going to give a presentation on exploration and production challenges of coal bed methane in India. Hemant Kumar Singh. Is he available? I think he is not there. May I invite Mr. Hemant Kumar Singh? So if he is not available, we will wind up this last technical session. Coming? Organizers, please confirm whether he is available or not. Okay. So we have come to the end of this day and technical session number 5. And in this technical session, we had one keynote address and 3 technical papers, and all have given a very good insight on the coal bed methane and coal, different aspects of coal mines. And we thank the organizers for having given us the opportunity to conduct this technical session.
Thank you very much.
Thanks for your patient listening.
So, with this session, actually, we are coming to the today's end of technical sessions today. And we had certainly had a very forceful presentations, one by Mrunal Kanti Mukhopadhyay himself, then by Meena Gupta, and the last one was also very interesting, though I think it needs to have more analysis, particularly regarding the tectonics of Tatapani Ramkola field and specifically Tatapani fault by Muhammad Mirajuddin Khan. So before the end of the today's technical sessions, I would request the chairman, keynote speakers here to come to the dais and have their memento. So Dr. V.A. Mende, I will request Rashtrapal Chavan to come and accept the memento on his behalf. I will request Mr. V. Mughal, who was chairperson for this session, to come over here and accept the memento. I will request the very interesting topic which was dealt by Dr. Mrunal Kanti Mukherjee to come over here and accept the memento for the keynote address. It is his, I think as far as Dr. Mukherjee is concerned, it is his homecoming because he was previously in GSI, and with all, we can say, experience of GSI, he has been serving ISM and certainly contributing a lot. And finally, I will request Dr. Hussain, a very distinguished scientist, geologist, head of the department, and my friend also, to accept the memento for chairperson. With this, we can say the formality from our heart. Today's session, technical session, comes to closure. All people are free to have dinner. Dinner is almost ready. And tomorrow's session will start at 9:30 morning. So all are requested to come at sharp 9:30. Breakfast is arranged here tomorrow morning. And persons who have not given the departure schedule, they please give departure schedule at the registration counter. Thank you all.